In Chapter 5, we will introduce the concept of loops. Let's suppose that we want to print the string Welcome to Java 100 times. At this point, we would have to hard code 100 print line statements. If we changed our mind and wanted to only print it out 50 times, we would have to delete 50 of those lines. If we wanted to prompt the user to ask how many times they wanted to print out the string, we have no way to accommodate. As you can see, this is tedious at best and impossible in the general case. But not to worry, that's exactly where loops come into the picture. Loops are programming constructs that provide for repeated execution of a block of statements. A single execution of the block of statements or body of the loop is called an iteration. We are going to learn about 3 types of loops. 2 of the loops are pretest loops, the for loop and the while loop, and 1 loop is a post-test loop, the do while loop. These 3 loops are equivalent in that we can use any of them to solve a given problem when loops are necessary, but as we will see, the nature of the problem and personal preference will determine which loop we use. So let's dive in. The while loop consists of the keyword while, a loop continuation condition expressed as a Boolean expression enclosed in parentheses, and a loop body enclosed in curly braces. The while loop is a pretest loop because the continuation condition is tested before the first iteration of the loop body. This is easily seen in the flowchart as the decision to enter the loop body is expressed as a diamond in the flowchart made before entering the block of statements representing the loop body. It is important to note that the parentheses that enclose the loop continuation condition are mandatory. Consider the program segment. This while loop is a counter-controlled loop because we use a variable named count to count the number of iterations through the loop. Based on the Boolean condition, we control exactly how many times the loop will execute. Let's trace the execution of this program segment. We must take great care when coding the loop continuation condition. There are 2 common errors that result from a mistake in the loop continuation condition. The first results when the loop continuation condition never becomes false, resulting in an infinite loop. The second, called an off by 1 error, results when the loop iterates 1 time too many or too few. We must use great care to ensure that the loop continuation condition will eventually become false, thereby terminating the loop, and also that the loop will execute the exact number of times necessary. Remember, it is very important to think before we code and to develop the algorithm that we will use to solve the problem. Another best practice is to code incrementally. Before coding a loop, consider writing the code for a single iteration. Once correct for a single execution, identify the statements that need to be repeated and wrap those statements in a loop. Finally, code the loop continuation condition and add any appropriate statements for controlling the loop. Test, test, test. Next, we will look at some case studies. Consider listing 5.1 in section 5.2. This program updates the addition quiz example from Chapter 3 by allowing the user to continue attempting to answer the addition question until the correct answer is given. You will notice that this is done by adding the while loop in lines 15 through 19. Pay special attention to the loop continuation condition. The loop body is only entered if the user entered the incorrect answer. Also notice that at the end of the iteration of the loop, a new answer is read in from the console. Eventually, when the user enters the correct answer, the loop terminates and the print line statement on line 21 is executed. Consider the following case study. We will write a program to generate a random integer between 0 and 100 inclusively and prompt the user to enter their guess until the user guesses the correct number. Each time, the program will tell the user if the guess is too low or too high. Take some time to look through the code in listing 5.2 and 5.3. Pay particular attention to how the random integer is generated and the loop continuation condition in the while loop on line 12. Note that this loop does not use a counter. We have no way of knowing how many times this loop will execute, but we can be confident, or at least hopeful, that the user will eventually guess the correct answer and the loop will terminate. In this case study, we will upgrade the subtraction quiz in listing 3.3. Previously, only one question was generated for each run of the program. In this updated version, we would like to allow a specified number of questions to be generated for each run and to report the number of questions that were answered correctly, as well as the time taken to complete the quiz. Consider listing 5.4 and answer the following questions. The while loop that begins on line 12 is a counter-controlled loop, so we can determine exactly how many iterations the loop will have. Based on the code, how many times will this loop iterate? How does the program determine how long it takes the user to test? How are the questions generated? Please watch the video note in the textbook resources. Consider listing 5.5. In this program, we allow the user to enter an unspecified number of integers and report the sum. The user enters 0 to signify the end of input. In this case, the number of iterations of the loop is not predetermined. Instead, it is signified by a specific input value. This specific input value, signifying the end of input, is known as the sentinel value. It is worth noting that we use a single variable, data, in line 12 to store the input value and sum in line 15 to store the total. Notice the loop continuation condition on line 16. As long as the data, the value that the user inputs, is not equal to 0, we iterate through the loop. When the user enters 0, the loop terminates and the sum is reported. It is vital that we remember that floating point values are approximations and therefore should not be used in loop control for checking equality. The do-while loop is a post-test loop, meaning that the loop continuation condition is tested after the first iteration of the loop. Notice the syntax of the do-while loop. The loop begins with the keyword do, followed by braces, the keyword while and the loop continuation condition in parentheses, and a semicolon. The statements forming the loop body are contained inside the braces. It is worthwhile to distinguish that the semicolon at the end of the do-while loop is mandatory, but the while loop does not end in a semicolon. Use a do-while loop if you have statements inside the loop body that must be executed at least once. The final loop that we will study is the for loop. The for loop is a pretest loop and uses a control variable to control the number of iterations. The syntax of the for loop begins with the keyword for followed by a pair of parentheses that contains the control structure of the loop, which is followed by a set of braces that contains the body of the loop. The control structure of the loop has three parts separated by semicolons. The first is the initial action, which usually initializes the control variable. When the control variable is used only in the loop, then it is declared in the initial action of the loop. Next is the loop continuation condition. Finally comes the action after each iteration, which can be a list of 0 or more comma-separated statements. The action after each iteration usually increments or decrements the control variable. The loop on this slide can be used to print out "Welcome to Java" exactly 100 times. Note that the control variable I has an initial value of 0. The loop continues as long as I is less than 100. When I is equal to 100, the loop terminates. A common mistake is to add a semicolon after the parenthesis in the for clause before the loop body. As we have seen previously, using the end-of-line style for braces can help us avoid this error.
Note the syntax error in the while loop. There should not be a semicolon after the closing parenthesis of the loop continuation condition. Much like our discussion of the if statement, this is often avoided by using the end-of-line style for braces. In the case of the do-while loop, the semicolon after the loop continuation condition is required. The three loops are equivalent. We can code a loop correctly in any of these forms. However, we will see that certain cases lend themselves to a particular loop construct. It is recommended that you use the loop that is most intuitive to you while taking the following into consideration. If you know the number of iterations, consider using a for loop. If you do not know the number of iterations or will be utilizing a sentinel value, use a while loop. If the loop body must be executed at least one time, use a do-while loop. Now let us consider how we might use loops to print out a multiplication table. We are not able to accomplish this using a single loop. We will need to use nested loops. Nested loops consist of an outer loop and one or more inner loops. Each time the outer loop iterates, the inner loop gets re-entered and loops to completion. Thus, to determine the total number of iterations, we must multiply the total number of iterations of the outer loop and the total number of iterations of the inner loop. See listing 5.7 in section 5.6 for the code implementing the solution to our problem. Notice the outer loop uses the variable I as the loop control variable, and the inner loop uses the control variable J as the loop control variable. Pay special attention to the fact that I corresponds to the row in the table while J corresponds to the columns. Additionally, you will want to consider the printf statement on line 19 to be sure that you understand the format specifier and corresponding item. You should not use floating point numbers in the loop continuation condition as it may cause errors. Please watch the corresponding video note in your textbook resources for a full discussion. In this case study, we consider the problem of finding the greatest common divisor of two integers. We allow the user to input two integers, n1 and n2, and report the greatest common divisor. Recall that 1 is a common divisor of any two integers, but it may not be the greatest common divisor. We can begin by initializing GCD to 1 and then iteratively checking if a number k is a common divisor for both n1 and n2, beginning at k equals 1. When we find another common divisor, we update GCD. This process continues until k is greater than either n1 or n2. Study the implementation in listing 5.9. Pay special attention to the loop continuation condition in line 17 and the Boolean expression in line 18. In this case study, we wish to predict how many years it will take for tuition to double if tuition increases 7% each year. It is key that we understand that if tuition increases 7% each year, then the tuition for the next year will always be 107% of the tuition for the current year, or tuition multiplied by 1.07. Listing 5.10 solves this problem using current tuition, or tuition at year 0, as $10,000. That means we must use tuition less than $20,000 as our loop continuation condition. Consider the printf statement in line 12. What is the difference in the %f and the %d format specifiers? What does the .2 in the %f specifier indicate? How could you modify this program to allow the user to input the current tuition? Break and continue are two keywords that can provide additional controls in a loop. Using these keywords can sometimes simplify programming. However, we must be careful not to overuse them or to use them improperly, as this makes a program difficult to understand or debug. We have previous experience with the break keyword in the switch statement. Recall that using break allowed us to immediately end or break out of the switch statement and transfer execution to the statement immediately following the body of the switch statement, which occurs after the closing brace of the switch statement. We can also use break in a loop to break out of the loop and immediately end the loop. When we use the keyword continue in a loop, we break out of a single iteration of the loop, and we continue the loop with the next iteration. Continue does not cause the entire loop to terminate, just the current iteration. Consider the code shown from listing 5.12. This program adds the integers from 1 to 20 and stores the result in the variable sum until sum is greater than or equal to 100. The loop terminates when the sum is greater than or equal to 100. Run this example with and without the break statement to understand the difference. Consider the code from listing 5.13. This program adds the integers from 1 to 20, but does not include 10 or 11 in the sum. When the number is equal to either 10 or 11, the continue statement ends the current iteration of the loop. The remaining body of the loop is not executed, therefore the following statement, which adds number to sum, is skipped. Run this example with and without the continue statement to fully understand its function. How would you modify the Boolean expression in the if statement so that only even numbers were included in the sum? This case study presents a program that determines if a string entered by the user is a palindrome and reports the result to the user. First, we need to understand exactly what is a palindrome. A palindrome is a string that reads the same forward, left to right, or backwards, right to left. The strategy used is to compare characters beginning with the first and the last character to determine if they are the same character. If they are, then we compare the second character and the second to last character, and we continue this process until we find a pair that doesn't match, in which case the string is not a palindrome, or all of the characters are checked, excluding the middle character if there's an odd number of characters, in which case the string is a palindrome. Consider the code to solve this in listing 5.14. We read in the string from the user on line 11 using the next line method in the scanner class. Recall that this is an instance method, so we must use the name of our scanner object and dot notation to call the method. We will use two variables, low and high, to indicate the indices of the two characters we are comparing. Since we begin with the first and last character, we initialize low to 0, the index of the first character, and high to s.length minus 1, the index of the last character. We initialize a Boolean variable, is palindrome, to true. Pay particular attention to the while loop in lines 20 to 28. Why do we increment low and decrement high? Notice that if the two characters that we are comparing do not match, we set is palindrome to false and break out of the while loop. Why can we use the relational operator for not equals? The exclamation point followed by an equal sign for the comparison.
Consider the problem of displaying the first 50 prime numbers in 5 lines, each containing 10 numbers. To solve this problem, we must understand what it means to be prime. An integer greater than 1 is prime if and only if its only positive divisor is 1 or itself. We need to determine whether a given number is prime, keep a count of the total number of primes we have found so we stop at 50, and display each prime number with exactly 10 per line. We can readily understand that we need a loop. But what should our continuation condition be? We need to keep a count of how many primes we have found and keep looping as long as our count is less than 50. Consider the code in listing 5.15. You will first notice in lines 3 and 4 that two constants have been declared and initialized to indicate the number of primes we are looking for and the number of primes to display per line. The variable count is initialized to 0 and used to count the number of primes found. The variable number is initialized to 2 and is the number we are considering as a possible prime. Notice that we have a for loop nested in a while loop. The while loop continues as long as we have not met the requisite 50 primes. For each iteration of the while loop, the for loop tests to determine if the number in consideration is a prime by testing to see if it has any divisors other than 1 and itself, and if such is found, it changes the Boolean is prime to false to indicate that the number is not prime. The next if-else statement prints the number out if it is prime. Notice the difference in the if portion and else portion of the if-else statement. What is the difference in the statements in line 29 and 32? Why are they different? Why is the condition count mod number of primes per line equals 0 used in the if statement?